and done the test, right? Cool. So at this point, we're entering the kind of review phase of the semester for this course. So these last 4 chapters that we're planning on doing, we're going to be, they're going to be out of order. We're going to do 14, 15, and then 12 and 13. But these are all topics that you did to some extent in Algebra 2. Now there'll be some additional, like we'll do a little of more depth and cover some other related ideas based on these things that maybe you don't do a lot of or any in your Algebra 2 class. But the main ideas are going to be largely review, which is a nice way to end the semester, right? With some stuff that's like, oh, this is familiar. So you're through what I think is really the hardest parts of the course, which is nice. Those of us that are the seniors, I got a couple in here, right? Who are my seniors? Just you twos. We'll have everything squared away for with grades and everything next week. We'll put in all the drops and stuff and do the doubling and all that jazz and see where we're at. And then we'll talk about, like, I don't think that we'll finish this chapter. I wouldn't, in fact, even if we finish, I wouldn't ask you to do the test for this chapter anyways, because, like, what am I going to do? We're going to do a test and then take the exam a day later. That's dumb. But we'll talk about, like, if you do have to take the exam, like, where would it end or whatever. Because I honestly don't know where your grades are at. I think you're both doing quite well, so I don't know that you'll really need to, but whatever. We'll cross that bridge if we have to. You know what I mean? Everybody else, when I do the drops for the seniors, I have to do them for everybody. The computer's not set up like that, so when I do that, all your grades will change, at least until and then you'll change again when we do the double or the retake, if you would like to do the retake. But that won't happen for use juniors until another month or whatever. But the drops will happen right away. And don't worry, the computer will update every time a new grade is entered. If their new thing should be dropped, the computer handles that all internally. So I promise it doesn't screw it up. It does it right. Okay. Cool. Anyways, or coolish, Kool-Aid man. So in chapter 14, we're going to be talking about rational functions. So this was a topic that you guys should have done in Algebra 2 and probably spent a good deal of time on. This is one of the more difficult Algebra 2 topics that gets handled. So let's just kind of start by reminding ourselves what a rational function is. So a rational function is just something, bless you. Nope, that was coughs. I retract my blessings. No blessings for coughs. Are you okay? You need a drinking fountain?
No, I choked on water.
That's embarrassing. Last thing you need is more water then.
Yeah.
I understand. A rational function is something that can be written in the form of P of x over Q of x, where P and Q are polynomials and Q of x is non-zero. So there is a term in this definition that we've used that we haven't really defined yet this year that probably is worth at least talking about, and that's polynomial. So can anybody give me an example of something that's a polynomial? Not an unreasonable question for a class of this level that you should be able to do this upon request. X squared plus 4 is a polynomial. Great. So another example might be
x squared plus x plus 4.
Okay, x squared plus x plus 4, sure. Do they have to have an x squared in them? No. What's another example without an x squared in it? X plus 4? Sure. Does it have to have more than one term in it? Nope. So like x is a polynomial. And shoot, even like 3 is technically a polynomial. How many terms can it have in it? What do you mean by, we have to be a little bit careful there. What do you mean by unlimited? Can't have infinite number of terms, but you can be as big as you want to be. So if you want 10,000 terms, that's fine. If you want 1,000,000 terms, that's fine. If you want 50 million terms, that's fine. As long as it's a finite value, no problem. If you have infinite terms, that turns into something else. That's a power series. It's a calculus topic. So a polynomial is finitely many terms. And in general, the way we define a single variable polynomial is we write something like this. So the a's are the coefficients, the n's are the exponents, right? We just have a variable times a constant to some power, plus or minus another constant times a variable to some power, et cetera, et cetera, et cetera. What's the one thing we have to be careful about here, or that needs to be specific about these n's? No, n can be 0. That's okay. That's what's going on over here, right? Like 3 is just 3x to the 0. So 0 is okay. But not all values of n are okay. Well, they all are real numbers, but there's real numbers that aren't okay for n. So the deal is n has to be non-negative and a whole number. So the exponent can't be a decimal or a unreducible fraction or even like a weird thing like a radical, like radical 2 isn't okay. And it has to be a constant, like you can't have the variable as your exponent, right? Does everybody kind of jog their memory there about what we mean by a polynomial? I think that's probably enough. What is when we talk about the degree for a polynomial, what do we mean by the degree of a polynomial?
Like that first exponent.
Yeah, it's the biggest exponent on the variable. It's not necessarily the first one, but the biggest one. And that's really only true for a single variable polynomial. Like if I have a term that has like x, y, and z in it, which exponent do you look at? You look at the sum of all three of them. That's the degree for that term. So if you have like x squared, y to the third, z to the first, then the degree for that term is 6. 2 plus 3 plus 1. Now that's not going to happen in here, but if we're talking, let's just talk. Cover our bases and be specific, right? And then what do I mean by the leading coefficient? We talk about a polynomial's leading coefficient. Yeah, so if I look at the biggest degree term, the coefficient on that is the leading coefficient. And if I ask about the leading term, that's the term, so the coefficient and the variable with the biggest exponent. Everybody okay? Which is a little light polynomial vocab review. I didn't write any of this down, we just kind of talked about it because it's review, right? And writing the definitions for some of these things is often like really difficult. It's much easier to just kind of like give some examples and talk about it or whatever. Okay. So first thing we're going to look at is domains. So let's say we have the rational function x plus 4 over 2x minus 1. And we're looking for the domain for this. Now, remember, the domain is the set of x's that when I plug them into the function, I get a real number output, right? So if I look at this function that I have, the operations going on are addition, subtraction, multiplication, division, right? That's the only things you see going on. Of those 4 operations, which one of them is the only one that's going to concern me if I'm talking about a domain? What's the only of those 4 operations that I can't do to anything? Divide, right? There's some things that I can't divide. Specifically, what gets me in trouble with division? Not dividing by a variable. Not dividing by a square root. What number?
0.
There you go. Dividing by 0. That's my problem, right? So I can multiply any 2 numbers together. I can add any 2 numbers together. I can subtract any 2 numbers together. Anything you give me, any of those operations is fine. Division, if you ask me to divide by 0, we got problems. Everybody's okay with that? So to compute the domain for this rational function, all I really need to make sure is that the x's that I plug in don't cause me to divide by 0. So I'm just going to take whatever my denominator is, set it not equal to 0. So basically I have, my domain should be all real numbers except for when x is a half. Now, we're not going to write our domain this way. We're going to write our domain using an interval notation because that's the way that we choose to do it. So everything except for 1/2, well, that starts at negative infinity, goes up to 1/2 but doesn't include it, and then it starts again at 1/2, not including 1/2, and keeps going all the way to positive infinity. So that's the way we would write our domain. Now, these values that x cannot have, we have a name for this that goes all the way back to the first chapter of the year. Does anybody remember the name for a value like this where the domain doesn't work? That's a discontinuity, right? So we've seen that rational functions can have one discontinuity. Could they have no discontinuities? Yes, what would that look like? Okay, what would the equation possibly look like? What if I said I have to put a non-constant in the denominator? Could you think of a polynomial there that doesn't have a solution when you set it equal to 0? I should say a real solution when I set it equal to 0. What if I did something just like x squared plus 1? Right? What's the solution to x squared plus 1? Plus or minus I. That's a non-real number. That doesn't matter for the domain. So this would have 0 discontinuities. The domain here would just be all real numbers. Could I have more than one discontinuity? Yeah. How many what's the maximum number I could have? Whatever the degree of the denominator is. Great, which is just has to be a finite number, right? You could have 10,000 discontinuities, 1,000,000 discontinuities, 1,000,000 billion trillion discontinuities, but not infinite. It has to be finite. Big as you want, but not unlimited. Let's just do another domain example where I have more than one of these real quick. Okay. So let's say we have 3 minus x over x cubed minus 4x. Well, just like before, we're just going to worry about where the denominator is equal to 0. How do I solve the equation, though, x cubed minus 4x equals 0? What do I do to solve something like that? Perfectly reasonable question for me to ask for students in this course at this level. Should be able to do this. Great, factor it. That's what I would do. So what's the first thing I would need to do to factor this?
Two numbers that add to -4.
Well, it's not quadratic, right? Yeah, let's start by taking out a greatest common factor of x. Very good. And the resulting polynomial is quadratic. So now you could look for two things that multiply to give you -4 and add to give you 0. Or you could just recognize that as a difference of two squares. How does x squared minus 4 factor? This should be automatic. X plus 2, x minus 2, right? At this point, since all the terms are linear, I know this is factored completely. Everybody agree with that? I'm sorry when I said term. I meant all the factors are linear. So what do I do next? We haven't solved anything yet. We've just factored it. How's that going to get me to a solution? Great. I can take each factor and set them equal to 0. That's called the zero product property. That only works, though, if the factors are equal to 0. If it's not equal to 0, you are up a creek without a paddle. You got to go back to the beginning and try something else, because the zero product property requires the polynomial to be equal to 0 to employ. So here I have 3 discontinuities, right? Okay. So how do I turn this into a domain then? -infinity up to... Which one of the 3 do I stop or do I encounter first if I start at -infinity? -2. Okay. And then after -2, which one do I encounter next? Zero. And then after 0, what do I encounter? 2. And after 2, there are no more. So we just go all the way up to infinity. So there's my domain. Everybody okay there? Okay. I want to circle back to this idea of discontinuities. Oops. Do you remember that there were 3 types of discontinuities? Again, this was something we talked about in the very first chapter of the year. That was a long time ago. There was infinite discontinuities. That's like your vertical asymptote. There was, I think the word you're searching for is removable discontinuities. That looks like a hole in your graph. That's not how I spell hole, though. Well, that is how you spell hole. It's the wrong hole, though. Okay. And the last type was a jump discontinuity, where it goes like something like that, where you have two distinct pieces that are not connected anymore. Rational functions can have either removables or infinite. They don't have jumps. How do you tell the difference based on our discontinuities, whether they're going to be vertical asymptotes or removable discontinuities? Do you remember doing that last year? Let's do it now, right? So let me give you two examples here. Okay, so I have two rational functions. I have f of x equals x squared plus 4x plus 4 and x squared minus 4. When I said and, I meant over. And then I have my g of x, which is equal to x squared plus 5x plus 4 over x squared minus 4. One of these has two vertical asymptotes. The other has one vertical asymptote and a removable discontinuity. Which was weird because they both have the same denominator, right? So they have the same, their discontinuities are at the same locations, but they are different. Joe, you said the first one is the one with the removable discontinuity?
Yeah.
How did you know?
Because the numerator simplifies and the denominator simplifies and they cancel out. There's some parts that cancel.
You meant that they factor, and then yes, great. So how does the numerator factor?
X plus 2, x plus 2. Denominator is x plus 2, x minus 2. So one of the x plus 2 is cancel. Paragon.
Wonderful. Yeah, I know what you meant. So we have this. So what's our vertical asymptote going to be?
-2.
It's going to be positive 2 because we're just taking the reduced denominator, setting it equal to 0. And our removable discontinuity is going to come from, how I find that? Do you remember? The piece that I canceled out is going to generate my removable discontinuity. But the removable discontinuity is a whole that has a location. It's an x and a y, right? How do I find the y coordinate for this? I plug it into the reduced version. So that's one removable discontinuity, one vertical asymptote. The removal discontinuity comes from the act of reducing. We've removed the factor x plus 2 from the denominator. Is everybody okay with that idea? Again, I think you do this, but it's probably pretty brief when you do it in your Algebra 2 class. Not a whole lot of depth to it. That's why I wanted to make sure we redo it now in a kind of a pretty thorough way. Because it's like, if I remember, it's just like a couple of problems or something where you talk about this. So if we try to do the same thing now with g of x, well, I know how x squared minus 2 factors. How does x squared plus 5x plus 4 factor? What does that factor to?
X plus 1, x, 5x plus 4.
Great. There I notice that nothing reduces. Everybody agree? So there's no simplifying that can happen. So to find the vertical asymptote, I just set the denominator equal to 0, and I get two solutions. And because I did no reducing, it is impossible for me to generate a removable discontinuity. Is that okay? Feel okay doing this? All right, here's a question for you. If I do reducing, do I always get a removable discontinuity? No. Let's look at this example. Notice that this is just the f of x from above. Oops. But I flipped it. So just doing the same thing that we did before. So my vertical asymptote should be just setting x plus 2 equal to 0. And if I did my removable discontinuity, what factor did I cross off? Still the x plus 2. Uh-oh. That's a problem, right? Because the vertical asymptote and the removable discontinuity are occurring at the same location. That shouldn't happen. It turns out there is no removable discontinuity because I haven't completely removed the factor of x plus 2 from the denominator. There was still one left over there, right? So even after I reduce, negative 2 still gives me a 0 denominator. Everybody see that? That's why it stays an asymptote and does not become a removable discontinuity. If I look at the f of x from before, if I look at my reduced version, negative 2 no longer gives me a 0 denominator. The negative 2 is a removable discontinuity. We removed that problem by reducing. Do we feel okay with this idea of like how to find these removable discontinuities? It basically boils down to anything that gets completely reduced from the denominator generates a removable discontinuity. Anything left in the denominator after reducing is just a vertical asymptote. Not a big deal, but, you know, like I think some exampling and kind of talking through that again is necessary. That's a piece that doesn't get really heavily covered in Algebra 2, if at all. If you don't remember at all, that's not uncommon. Okay. Next thing we're going to talk about is next thing we're talking about is finding key features within our rational functions. So one thing is we're going to be looking for vertical asymptotes. The way we write our vertical asymptotes is like an equation for a vertical line. So it's x equals something. So to find that vertical asymptote, you set your reduced denominator equal to 0 and solve. Again, you could get no vertical asymptotes. That's okay if your solutions are all imaginary or something. That's fine, that happens. So removal discontinuities, what did we do to find that? We set any factors completely reduced from the denominator equal to 0 and solve. Then plug those solutions into the reduced function to get the y coordinates. Okay. So that's just kind of me summarizing just what we did before, right? The other key features we're going to be interested in are the zeros. That's the same thing as the x-intercept. So that's like, again, that's a point. Like something comma 0. How do we find the 0 for a rational function? Does anybody know how to do that? Or remember how to do that?
It's not like what we just did last chapter, right?
No.
I was finding the roots of it.
Yeah, you're finding the, well, that was just like finding the roots for a complex number, right? So just taking like the square root of 2 plus 6i or something. When is a fraction equal to 0? When the numerator is 0. So what are we going to do here? Close, set the reduced numerator equal to 0 and solve. But there's still one thing we have to check. What could happen there?
It could be a irrational number.
That's fine. Irrational is no big deal.
Or it could be an imaginary number.
That's fine. I just mean it wouldn't exist. That's okay. They could have no zeros. But there is something where we get an answer and it's not right. Let's go back and look at this example that we just did right here. So if I look at the reduced function, what would I get if I set the numerator equal to 0 and solved? What value do I get? If I take that guy that we just did, set that equal to 0 and solve. The numerator. I get -2, right? But what's my removal discontinuity at? Right. So is there a 0 there? No, because what is actually at that location instead of a point? A hole, a discontinuity, right? So that's the other thing we have to be careful about. So we do have to then check these solutions against our removable discontinuities. Right, so you just have to make a quick check to make sure your zeros aren't already claimed as a removable discontinuity. Now, to be honest with you, do you think that's going to really happen? Where Mr. Kulik's going to give you a problem where you have a 0 that's also removed as continuity? Probably not, but like, that's something that can happen, and we should talk about it, right? Like, it's important that we cover our bases. I want to be precise and give you like the whole picture, the complete answer, just not like, we're not going to talk about it because it's not going to happen for us. We're going to talk about it if it can happen. I may not expect you to deal with it if it can happen, but it's important that we, that we do it the right way. You know what I'm saying? Give you the full picture rather than just like the expedient, like this is what you need to know. All right. Y-intercepts. How do you find a y-intercept for something? Any function.
Set x equals 0.
Yeah. And in this case, where do we have to plug 0 into? We need to do it to the reduced function. And then we just evaluate, right? But what do we have to be careful about? What do you mean 0? Nah. That had already been claimed as a vertical asymptote if it could happen, or a removal discontinuity. It's the same thing as the zeros, though. You could have a removal discontinuity at x equals 0, right? So that's the thing that we have to check again, is that point where the y-intercept lies is not already claimed as a removable discontinuity. And then the last thing that we're going to worry about are these end behaviors. So these end behaviors are going to be written as lines, or, well, equations anyways, like y equals yada, yada, yada. Now this is maybe the trickiest part here. So there's 3 cases. So the first case we'll talk about is where the degree of the numerator is less than the degree of the denominator. So in that situation, you're always going to have a horizontal asymptote at y equals 0, although I'm going to put a little asterisk here. To just say that we're going to still call things asymptotes, even if the function crosses them, as long as it's just crossing it like finitely many times somewhere in the middle of the function. So say that that's like our asymptote. I would still count it as an asymptote even if this kind of thing happens, where the function crosses it, but at the ends, it's still acting like an asymptote, right? We're still going to call that an asymptote. This is just the calculus definition for a horizontal asymptote, where we just need that asymptotic behavior at the end. Okay. Our next case is when the degree of the numerator equals the degree of the denominator. If the degrees are equal, then we get a horizontal asymptote at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So LC is just me abbreviating leading coefficient. And again, it's okay if the function crosses that asymptote, once or twice or whatever in the middle, finitely many times. We just care about it still continuing to behave itself at the ends. The last case is the degree of the numerator is greater than the degree of the denominator. So here we're going to get a polynomial asymptote at y equals the quotient of numerator divided by denominator. How do you get that quotient? It's the result from polynomial division, right? You have to do polynomial division on the numerator with the denominator. The quotient part is going to give you the equation for that asymptote. Typically, in this course, it would be a line, although it could be a quadratic, it could be a parabola, or a cubic, or, could be any kind of polynomial. That's why I'm going to refer to that as a polynomial asymptote. More often than not, we'll call it a slant asymptote because it's just going to be a diagonal line. But need not be. Is this stuff all kind of sounding familiar-ish? I think in Algebra 2, when you look at this last case, it's always a diagonal line. It's always a linear polynomial, your asymptote. Here, I think in the homework, you'll see some examples where it might be quadratic. That's okay. So let's do some examples running through these. And then we'll do some limit notation examples while we're doing this. All right. So let's say we're asked to identify the key features for x minus 1 over x squared minus 4. First thing that I'd want to do is factor and see if there's any reducing to do. The numerator is linear with leading coefficient 1, so there's clearly no reduce or factoring I can do to the numerator. The denominator is x squared minus 4. We factored that like 4 times already, so I'm just going to write down the way it factors. And we notice that there's no reducing to do here. That's fine. So what are my vertical asymptotes going to be? 2 and negative 2. Anybody with a question as how we got that? Setting the denominator equal to 0 and solving. What are our removable discontinuities going to be? Anybody? Removable discontinuities, what are those? Good. Why? You didn't do any reducing, right? If you didn't reduce, you can't get a removable discontinuity. That simple. Oh, okay. I like that. How about zeros? What are those going to be? One zero. How'd I get that? Set the numerator equal to 0 and solve. Yup. Good. What about the y-intercept? What's that going to be? 1/4. Great. We just set the x's to 0, so you end up with -1 over -4. 1/4. And then these other asymptotes. Which situation is this? What's the degree for the numerator? The degree for the denominator? 2. So which situation are we in? The first one. Right? What happens here? We just get the y equals 0 horizontal asymptote. Every time the degree of the numerator is less than the degree of the denominator, 1 is less than 2, we just get y equals 0. All right. Let's take a minute here and just kind of sketch out what the picture of this is going to look like, or how we can use these key features and then a little bit of computation to sketch a decent picture of our function. So I'm going to start by drawing in my asymptotes. So I got my 2 verticals and then my 1 horizontal. I'm going to draw in my zeros and my y-intercept. Notice right here, I see that I'm going to be at least intersecting the horizontal asymptote, if not crossing it, right? Because I had to draw that 0 in there. That's on the y equals 0. Okay. So what I need to do now is I need to figure out what the rest of the graph is going to look like. So I'm going to do this from left to right. So I need to figure out, is my graph going to look like this? Or is it going to look like this? Because I know that I don't cross that horizontal asymptote any place other than at the 0. And I know I never cross a vertical asymptote. So what I'm going to do is I'm going to figure out what is happening as I get really close to this asymptote on the left-hand side. So what I'm doing here is I'm calculating the limit as x approaches -2. And then in the exponent for the -2, I'm going to put a minus sign, which is saying I'm looking at what's happening as x approaches -2 from the left, where the numbers that are smaller than -2 live. For my function f of x, I'm going to see what that limit is. Now, we haven't talked about how to do this algebraically, and we won't in this class. It's a calculus topic. If you take AP Calc next year, we'll do it like in the first chapter. We work on limits, a whole mess. But we can do this numerically. So that's what I'm going to do here right now. So to do this, I'm just going to go ahead and type my function into the y equals menu. So just x minus 1 over x squared minus 4. Notice that I'm using that fraction command. Highly recommend you do that to do these kinds of problems. And then I'm going to press vars, go over to y vars, from function, select y1. And I'm just going to plug in some values that are smaller than -2, but are getting progressively closer and closer to -2 to see what the function should be doing there. So maybe I'll start at -2.1. And then we'll get a little bit closer to -2, so we'll go -2.01 and get a little bit closer to -2. So -2.001. And I notice in each case, what is happening? the value of the function is decreasing, right? So what is this limit heading towards? Negative infinity. So what's happening to my graph? I should have the blue picture. The graph should be pointing down. Everybody's okay there? I now need to do the same thing on the other side of negative 2. So that's going to be the limit as x approaches negative 2. But this time I'm going to put a plus sign in the exponent. That indicates that it's going to be approaching negative 2 from the right, using numbers that are bigger than negative 2. So I'll do the same thing in my calculator. I'm going to keep pressing second and enter once I've retrieved that y1 command and just make some little edits to it, because it's like a lot easier than all the menu hopping that I have to do to get there. So I'll start with negative 1.9 and then get a little bit closer, negative 1.99, and get a little closer again, negative 1999. And I noticed here that things are getting bigger and bigger and bigger, so this is going to positive infinity. So I know that that part of the graph has to look like this. And I'm going to go ahead and connect it through my y-intercept into my 0. And then I'm going to figure out, doing the same thing, what's happening on the left side of this asymptote. So that's limit as x approaches positive 2 from the left. So again, I'm going to start with numbers that are a little less than positive 2. So 19, 199, and 19999. So again, I'm seeing these are decreasing the whole time. Yes, certainly. So this is going to negative infinity, or that the arrow on my function should then be pointing down. And then I have one last piece to check. What's happening on this side of my asymptote? Purple. So that's going to be the limit as x approaches 2 from the right of f of x. So we'll start at 2.1, and then we'll do 2.01, and then say 2.001. And I notice everything keeps getting bigger and bigger and bigger. So I know that part of the graph has to look like this. And we're just going to then follow the two asymptotes. There we go. So notice that each of these arrows on my function corresponds to some kind of a limit. But I haven't written a limit for this arrow yet, or for this arrow. What would I write the limit for this green arrow, the light green arrow that I've circled over here? It's the limit as x approaches negative infinity. Great. Of f of x. And what y value is the function heading towards then? 0. Very good. Which happens to match my horizontal asymptote, right? So that's the calculus definition for a horizontal asymptote, is the value that the limit as it approaches positive or negative infinity goes to. So if I look at the light blue one that I've circled here, that's the limit as x approaches positive infinity of f of x, and that's equal to 0 as well. Everybody's okay with this? We should be able to use these limit notations. That's an expectation for this chapter and for this course. So we haven't done a lot of that yet. This is a good chapter to do it because there's lots of end behaviors for these rational functions, because you have, in this problem you had 6 arrows. So you have 6 limits that you can write, which is nice, gives you a lot of practice kind of doing that and getting used to the notation. It's a nice natural fit. Okay, let's do another example here. So I have the polynomial, or the rational function 2 minus x over x plus 3. What are my vertical asymptotes going to be? Negative 3. Good. Notice that there's no reducing to do on this. I guess I didn't bother to point that out before we started, but you see polynomials that have degree 1. There's probably not a whole lot you're going to be doing there. Remove discontinuities. Yep, none of those. Zeros. Yep, just the numerator set equal to 0. Well, you divide by -1 afterwards, so it becomes positive 2. Y-intercept. Great. And then my other asymptotes. What's the degree for the numerator?
1.
The denominator?
1.
So they're equal. So it's going to be the leading coefficient of the numerator, which is
1.
-1, and the leading coefficient of the denominator, which is
1.
positive 1. -1 over positive 1 is just -1. So if I were to draw this again, 1, 2, 3, and then y equals -1 is down here. I have 2, 0, and 0, 2/3. So I would say right now I have enough information to draw this piece. Right? That's really the only way that those are going to connect. So last thing I have to do is just figure out over here what to do by looking at the left side of that asymptote. So again, I'm going to do this numerically. So I'm just going to go to my calculator. I'm going to enter in my new function, which was 2 minus x over... Oops. Boogers. I didn't think it would be smart enough to do that. Yeah, of course. And it was x plus 3. So we'll start at -3.1. 3.01, and at this point I'm pretty positive what's going on. Looks to be the negative side. So there's my picture. No big deal there, right? Should look just like a simple rational function that you remember graphing from last year. Ideally, maybe not. All right. Let's say we have Okay. So we have x squared minus 4x minus 5 over x plus 2. Here I notice there is some factoring I can do. Let's start by doing that, just to make sure there's any, see if there's any reducing. How does x squared minus 4x minus 5 factor?
X plus 2.
Nope.
X minus 2.
Nope. Has to multiply to give me negative 5.
Oh, x minus 1.
Nope.
X plus 1. X minus 5.
There you go. It's been a minute, right? It'll come back. But again, to reiterate, like in this chapter, you will do a lot of factoring of polynomials. If you don't feel great about that, try to brush up a little bit and ask some questions if you're still kind of feeling uncertain. If you really need to, I'll get out the touch and tell from my closet here and get the times table where it's like 3 times 5, 21. Or, well, 3 times 7, 21. 3 times 5 is 15, you dumb skull. Anyways, all right, so no reducing to do, though. That's the point. Let's rock and roll. Vertical asymptotes. Negative 2. Removal discontinuities. None. Zeros. Negative 1 and 5. Y-intercepts. 0, negative 5 halves. And my other asymptotes. This is the tricky spot because the numerator is degree 2. The denominator is degree 1. That falls into case 3, where we need to divide, or we need the quotient from the polynomial division. Remember back to Algebra 2, there are 2 methods you would have talked about to do polynomial division. What were they called? Synthetic division was one, and the other one is long division, right? So it looks like the long division algorithm you learned in elementary school. Which one is the one you'd prefer to do? Synthetic. It's much quicker, takes up much less space. What's the hitch? You can't do it every time. What do you need to have in order to do synthetic division? The divisor in your synthetic division problem has to have 2 things. Degree 1 and leading coefficient 1. If you don't have that, what are we going to have to do? Long division. Now let's look at here. What's my divisor in this case? X plus 2. That's degree 1 with leading coefficient 1. So I'm going to do synthetic division here because I'd much prefer to do that if I can. Keep in mind you can't do it every time. So we set up the synthetic division bar. And what number goes on the outside over here? How do I get that number? I set the divisor equal to 0 and solve. So just negative 2. What numbers go on the inside here? The coefficients from my numerator. What do you have to be careful about when you write those coefficients for your numerator in? The signs, sure, but there's something else.
The order.
Sure, the order, but there's something else that I'm thinking about that's very commonly missed. What if this was just x squared minus 5?
Oh, I need to put a 0.
Need to put a 0 if I skip a term, right? Now, if you're doing long division and you don't put a 0 there, still recoverable. You have to pay attention and notice that, like, hey, those are 2 things I can't subtract that I've just lined up. But if you forget the 0 with synthetic division, there's no recovering from that. It will just be a big mess and it's all going to be wrong and you'd have to start all over again with the 0 there. So be careful on that. It's easy to forget. That's why I'm making a big deal now. Okay, so this is all set up. How do I start? Bring down the first number. and then I multiply the number on the outside to the number on the bottom, and write it in the next spot, and add down. And then just repeat. Oops. So those numbers at the bottom somehow tell me what's going on, right? What do those numbers at the bottom tell me? Not quite. If I read from right to left, the 7 is the remainder, and then it's the constant term, and then it's the x coefficient. So what this is saying is that x squared minus 4x minus 5 divided by x plus 2 is equal to x minus 6 plus 7 over x plus 2. This is the part that we care about. That's our polynomial asymptote. That's the worst one. It requires the most amount of effort to squeeze that out of there. Although if you get to do synthetic division, it's not so bad. But there's a lot of stuff that we had to remember from Algebra 2 there, right? All right, let's try to squeeze a graph out of this now. So -2 and then how do I graph y equals x minus 6?
Start at -6 with y-intercept.
Okay.
Just go with 1 over 1.
Sure, you could do it that way. 1, 2, 3, 4, 5, 6. What I like to do is I like to use a point that's further apart, because neatness kind of counts for this. If I have 2 points that are really close together, if I have a little bit of error, it makes a big error. So I'm going to pick the x-intercept. I'm going to pick x equals 6 and plug that in to get y0. So another point on this line would be 6, 0. 1, 2, 3, 4, 5, 6. Although, to be clear there, Nolan, what you said is absolutely correct. Just from a logistic standpoint, I wanted to do something else because I know my own penmanship. All right, so there's that. My asymptotes are in. And then I have zeros at -1 and 5, and I have a y-intercept at -2.5. So right here, I can tell that, well, the only way to connect those 3 points there and stay between the asymptotes is it'd have to look like this, right? That's great. I love not having to spend a lot of time. What I need to do now is figure out which one of those two I should have, right? So all I'm going to do is look at this side of my asymptote and see what's going on. Do you guys feel okay me doing how to do that in the calculator? I'm just going to cut to the chase then, because I'm just sick of doing it in the calculator over and over again. This is the one. Okay. All right. Little bit of limit review now. So I'm just going to label each of these arrows 1, 2, 3, 4. And just off to the side, we're going to write the limits for each of these. Just for some more practice. I know we haven't done a lot of this, so I want to squeeze a little bit more in here. So for number 1, this is the limit as x approaches.
-1
Yes, good. Of f of x equals, what y value is that arrow pointing towards? No, man, zero's way up here. That arrow's pointing to negative infinity, right? Yeah, that's all. It's pointing down-ish, but down. 2, that's the limit as x approaches. Well, what x value is that at?
-2.
Okay, but what side of -2 is it on? The right or the left?
Left side.
The left side, so we're going to use a negative sign in the exponent to denote that. And which way is the arrow pointing? Down. Infinity. Very good. Yup, you're getting it. Again, it's not hard, it's just getting used to the notation, right? The notation is new, but it's like, if you understand like how to go from picture to notation, notation to picture, it's really quite easy. There's nothing tricky that we're doing, no calculation we're doing. It's just understanding like how to translate from picture to notation, notation to picture. All right, 3. That's the limit as x approaches.
-2 plus.
Great. And then we have our f of x equals positive infinity. Everybody cool? Is this getting clearer-ish? Okay. And then 4, the limit as x approaches. What's this one at 4? 4 is here. It's kind of hanging off the screen. What is the x approaching for 4? Positive infinity is correct. Then I have my f of x equals, and which way is the arrow pointing? Up or down? Up, so positive infinity. How do you guys feel on doing these limits? Hopefully a lot better than what we started, right? As we've done more and more examples, hopefully it's getting clearer and clearer and clearer. It's one of these that like once you get it, and it's like, okay, I got it, no big deal. But it can be a little bit tricky. We have 5 minutes left. I have one more example that I'd like to do, but I'm going to save it for next time. At this point, you guys should be able to do up through 24 from the problem set. And all that is up in your OneNote. So just like the examples that we've done in class, okie dokie. Alrighty.